Welcome to this recorded video for the Part C lecture notebook for the third module. In this one, we will actually be focusing on what Python modules are. And we will see an example called differences that involves approximation of derivatives. Now we will be using NumPy and importing it in the standard way as NP, so make sure you run this first code cell at the top of the lecture notebook. And for our objectives, we will understand what a module is in Python and when and how to import and use it. You will see how to create your own module. In fact, that's one of the activities you are asked to do. We will implement the differences module to approximate derivatives of functions. We will understand the basic importance of derivatives in the context of computational and data science. And we will also begin to see widgets, which allow us to add more interactivity to our Jupyter Notebook environments. Now, there are 3 activities, including the summary activity in this notebook. You will see how to make and use your own module, which is how we will end this first recorded video for this notebook. And then I will have a second video lecture that will discuss widgets, and it will also discuss the second main activity in this notebook where you have to do some plotting. So what is a module in Python? It is a file containing Python definitions and statements. The file name is the module name with the suffix .py appended to it to stand for a Python file. Within a module, the module's name is available as the global variable where you have 2 underscores name with 2 underscores. You often don't need to worry about this, but it's just a technical point that's worth noting. When should you use a module? If your script gets very long and you want to have easier maintenance, you should use a module. Or if you want to reuse a function in several programs or notebooks or scripts without having to copy and paste that function definition across the different files, then it's best to just use a module and import it. Much like we just import NumPy as NP because we are always using NumPy, we might find several times we're using the same type of function, and in which case we should probably put it in a module. And there's also some performance reasons to use a module. Now we will look at an example. The differences module contains several functions for approximating the derivative of a function using finite differences. Now this link right here will take you to the Wikipedia article on derivatives. A derivative, more or less, involves just taking it, for our purposes, the slope of a tangent line, a line that intersects a function at one point. And if you are not familiar with derivatives, you don't have to worry too much about understanding this, other than I would say you should read, and this is a link that I write right here, provide for you. If you are unfamiliar with the concept of a derivative, you should probably take about 15 minutes to read through this wiki article on differential calculus. It has a nice, I'm going to scroll to the top, a nice introduction to it. So it talks about the geometry. I would say for the 15 minutes, start here, read the top of this, and then read about the derivative here in terms of how it shows the approximation and what the derivative looks like, the slope of a tangent line, this derivative notation right here, as you move the tangent line, the point of tangency of the line along a function, so you can get some intuition about what the values are. The important understanding of approximating a derivative comes down to finite differences. This was the link that I provide right here. And so I would read just the basic types of derivatives, this finite differences. Start right here, the basic types and this relationship to derivatives that we have. Basically, with a function, the way we would approximate the slope of a tangent line at a point, let's say at a point x, is if we said, I want to know what the slope of a tangent line is there, we would evaluate the function at the point, and we would evaluate the function at a nearby point. And we would consider the line that goes through those 2 points. That's called a secant line. And then we would just compute the slope of that line. And that would give us an approximation of the slope of the line that just intersects at this one point. And by reducing the distance of this new point on the x direction on the horizontal axis from the point you're interested in, as that delta x value decreases towards 0, you can either, with a forward difference, meaning you add a positive delta x, or you subtract a positive delta x to get a backward difference, these will give you first order approximations to the slope of the derivative, to the slope of the tangent line. Excuse me, that's what I meant. The derivative is the slope of the tangent line. And then a center difference approximation would just use the evaluation at both of these points and take the slope of that line. So it gives you the idea of the difference graphically here. Like I said, it's worth reading it. In the end, the computation is actually rather simple. What you see is something like this. You take f, you add x plus h. H is the difference away from x that you use. And you subtract f of x and divide by h. That's the slope of a line evaluated at x and x plus h, because here's the difference in the function values, and here's the difference, x plus h minus x just gives you h in the denominator. This would be a forward difference approximation to the derivative. The backward difference approximation, I believe it would, I'm not sure if it shows it here, maybe it does not, is we would just take f of x minus h here, and then the center difference would be where we evaluate at two values. I think it's best to show this actually in our differences module. You will see the computation is really simple. So you need to make sure in your Jupyter lab that you have this differences.py file, which is provided on Canvas along with the notebook here. You need to upload this to the lab and have it in the same directory. And if you look at the contents, you see here's the forward difference approximation, and I have some default keyword values for the x and h values, and you pass it a function f, and then here's the approximation of the derivative, f of x plus h minus f of x divided by h. It is not a complicated computation. The backward difference, you again give it a positive value of h, but here you see you do the following. You take f of x minus h divided by h. And you can, the reason that you have the subtraction here is because you would actually divide by negative h. I just brought that negative into the numerator in this computation. The center difference approximation has f of x plus h minus f of x minus h, and then the difference between the two inputs is a distance of 2h. Again, you can, if you come to the finite difference approximation and you look at this picture, you can start to see exactly how we get these computations in terms of taking the slopes of these different lines that are trying to approximate the line of tangency at just this value of x. So the overall computations are not too hard. You really don't need to understand calculus in any great way or derivatives to do any of the computations in this class. You just need to use this differences module throughout the class at various points. But I do still encourage you to read about derivatives, and in particular in this differential calculus section, to read through in about 15 minutes this part right here that goes through some basic computations. It should take you probably about 15 minutes to read through. You can skip over the history of differentiation, but you should really read about the applications of derivatives in terms of optimization, and I think some of the physics, and there's differential equations. You can see why we care about derivatives so much. And actually, it's a good reason why we study calculus, is so that we can solve optimization problems in particular. Those are very practical. And we'll see in computational data science, this comes up all the time when we want to optimize things. And in data science, we're often trying to optimize the parameters of a function. For instance, even regression, where you're trying to reduce or minimize the sum square errors, the errors in your approximation. You formulate it like a minimization problem, and you can use calculus to solve it. But we won't dwell on that now. It's just something that you should know what the applications are and why they're important. Now, here I'm going to just go ahead and set up our matplotlib environment. I do suggest that you try this matplotlib widget, since we're talking about widgets here, after you've run through everything. Don't do it yet. Let's run through everything first, and then you can play around with this, because you'll see there are some limitations and some weirdness that comes in when you start to use that. So I think this is just the better option in general. But here we go. I import differences as diff. Just like we import numpy as np, I want to import differences as diff so I don't have to write differences each time. I can just use diff now. And then, of course, I want to plot some results to explain derivatives graphically. And this is where we will import our standard PLT from pyplot as PLT from matplotlib. So we run this cell, and now we've imported this module. So these three functions, the forward difference approximation, the backward difference approximation, and the center difference approximation, are now available with our standard dot convention using the diff.forward difference, diff.backward difference, and diff.center difference. Of course, here I have the actual function names here. Oops, I'm sorry. Just scroll out in here. I'm just using those function names. And the autocomplete will allow you to do those. So here what I'm doing is I just created a function. I call it my function. And it's just to provide some interesting plot. And then I actually computed its actual derivative. You do not need to know how I got this. This is just for illustrative purposes. So I'm going to run this cell. Of course, if you do know some calculus, you'll see that taking the derivative of this, which is just e to the negative x squared times sine of pi x, the derivative of that is computed just using a combination of chain rules and product rules. All right, here is how I would compute a forward difference approximation to f prime. You usually use f prime. Again, if you look in the derivative and you look at this notation for derivative, they have some, here we go. Lagrange's notation is f prime of x. That's typically how we denote the derivative for a function f, is f prime. So the forward difference approximation, I'm passing it my function. So I'm going to compute the approximation. I'm going to compare it to the actual derivative. That's, again, in this differences module, you give a function f as the first input. It's the positional argument here is the first input to all of these functions that are approximating the derivative of f. Then I'm going to overwrite some x value and h value because I want to compute them at actual points instead of these default values. So for each of these, I pass, for the forward, backward, and center difference, I pass my function. I give it this lens space of x, all these different x values. And then I start with an h value of 0.2. This again is the step size that I use. It's in some of these places, they'll call it delta x. In other places, they'll call it h. So here in this picture, for instance, this is in the derivative part of Wikipedia. Here's the secant line. Here's this nice computation showing how the secant lines approach the tangent lines. So again, you should spend 15-20 minutes looking at these Wikipedia pages just to familiarize yourself or remind yourself about derivatives. So I'm going to use kind of a large h value, and then I'm going to say try some smaller values. All right, so let's run this. That now approximated the derivative of f at all the x values, at all 100 points of x values between 0 and 3, evenly spaced, with an h value of 0.2. Now, I create a plot here, and I have subplots to it where I first plot the function, and then I plot the actual derivative that I used calculus to compute. And then on that same plot, I will plot all of the derivative approximations. I include a legend, so I'm labeling all of these plots. And then I will also plot the x-axis, the typical type of x-axis you would have for reference, because we're going to make some points about this. And then in a third plot, I am going to plot the error in the derivative approximation. So I'm taking the forward difference approximation, and I'm subtracting from it the actual derivative. And then I'm similarly doing that with the backward difference approximation and the center difference approximation. And again, I have labels and I have a legend. So let's run that. So here's the function. It has some variation from 0 to 3 that's somewhat interesting. It's e to the negative x squared sine of pi x, like I said. That's in the title that I set here. And here's the different derivatives, and the derivative and the approximation. So in blue, here's f prime. I'm zooming in here. You can see that it's coming down. Initially it decreases, then it comes up, and then it kind of dies out towards 0. And if you look, the center difference approximation is often the most accurate. There's a little bit of error between it and the blue curve, but it seems to generally be better than the forward or the backward difference approximation. And the forward and the backward difference approximation seem to over or underestimate the derivative of the function in kind of equal amounts, which is something you can also see in the error. The error in the forward difference approximation is generally, if it's generally positive, and the backward difference, it's generally negative. So there are exceptions to this, but it's kind of generally the case. And the error in the center difference approximation is typically better than either one of these, but there's sometimes reasons you don't want to use the center difference approximation, which you can, again, read about on those wiki pages. So you can see quick convergence to the derivative if I start decreasing this h value. So I started with 0.2. Let's now try 0.1. And here you see The center difference approximation is really close to the actual derivative now, and the overall error has been reduced. Now, this plot looks very similar, but let's look at the scale. It's about negative 0.4 to 0.4 on that range, a little bit above and below for the forward and backward difference approximation. But let's go ahead and go back to 0.2 so you can see the level of error originally. There it's going from negative 1 to 1. So we reduced the error in about half by reducing the step size by half. The h is typically referred to as the step size. So by reducing it from 0.2 to 0.1, the error was reduced by half. And that's when, if you recall, I said the forward and backward difference approximations are first order approximations. So they generally reduce, the order of magnitude of the errors is reduced by the same way in which you reduce the step size. So if we half the step size, we half the error. So let's now go to 0.1 again. So there's that error. It's, about, I would say negative 0.5 to 0.5. We reduced it in half, so this is pretty accurate. Look what happens if you go to 0.01. All the derivatives appear to agree. And now when you look at the errors, in fact, you see that it goes to about negative 0.04 to, or I would say negative 0.05 to 0.05. It goes above those tick marks. So it's reduced by an order of magnitude. We went from about 0.4 before to 0.04. What did we do with the step size? We reduced it from 0.1 to 0.01. So we're seeing more and more accurate, but the scaling of the plot is making it so the plots don't maybe look like they're so different. You have to pay attention to the vertical axes to see how things are changing. Now, what happens, if we go to, let's say, we 10 to the negative 7th power. So that's, again, the scientific notation for that. Now the error is very, very small. Okay, we reduced the error again by 6 orders of magnitude from what it was before, because we went from 0.01 to with a bunch of others. Or hopefully you get the idea. It all seems very accurate, and the error seems very small. When you look at the plot, it's kind of annoying that 1 e to the negative 7th is showing up here. So this is 4 times 10 to the negative 7th, 2 times 10 to the negative 7th. That's the way to read the values on the y-axis for these plots. You have to pay attention. If there's a number that shows up here, it's going to tell you what the scale is in terms of orders of magnitude. So let's see what happens when we go to 1 e to the negative 12. The error went up. It's no longer has 7 zeros. It's not 10 to the negative 7th. So I think it's not that many zeros. It's gone up. It's 0.00015 now, and there's a lot of noise here at this scale. The error went up. What's happening? Let's see what happens as we continue to reduce h. Let's go to 1 e to the negative 15. The error got even larger. So now it's 0.15 instead of 0.00015. So it increased by 3 orders of magnitude, even though we decreased the step size by 3 orders of magnitude. So you kind of go like, well, what's happening? The error is getting even worse. And you can see in this plot, it's definitely starting to get visually choppier as you approximate the derivative. And you say, well, what happens if I go to 1 e to the negative 20? So there's your derivative approximations, which look like complete nonsense. And here's the error in your derivatives. All of them. The reason you don't see 3 colors is they're all lying on top of each other. And the error is completely insane. It's basically what's the value of the function, because everything here was 0. Well, this is because of the finite precision arithmetic that a computer can handle. You've reduced h so much. When you take 1 e to the negative 20, this is below the type of floating point precision that the computer is expecting for the types of numbers it's computing. And it's basically saying the function values, the difference in the function values is 0 because there's not enough precision in the arithmetic. And that's why it's saying the slopes of all the lines are of all these secant lines with that h value is 0. So there's a limit to what you can compute, even though the theory of a derivative is that you would take this h value and send it to 0, take the limit as it goes to 0. Computationally, what you're going to be kind of limited by in terms of the best accuracy you can expect, doing it in the wrong spot, is right around 1 e to the negative 7th. Because right around 1 e to the negative 7th is around, for standard floating point numbers, the square root of what machine epsilon is. which is about the smallest number that you can distinguish from zero in a typical floating point number. So that's just something to be aware of, is that there's computational limits to calculus. You cannot on a computer actually compute the limit as h goes to zero. You have to settle for an approximation for h values that are not maybe as close to zero as you would like, but they're as close to zero as you can computationally get with reliable computations. So that's often something around the square root of machine epsilon as a good rule of thumb. You can increase the precision of your floating point arithmetic, but in practice, this will only get you so far. This is just something that's studied more in depth in a class like numerical analysis. I just want you to be aware of it now. So moving on, there's some important questions and answers and takeaways about derivatives. Do you need to know how to compute derivatives in this class? Again, I emphasize no. You can and you will just use the differences module in this class. We will be using this in the 4th module when we do some computational applications. You never need to know how to actually compute a derivative. The conceptual and computational aspects of derivatives are briefly discussed in this video, and we will hit upon important application and takeaway points of the concepts of derivatives, but you do not need to know how to compute derivatives. You just need to know how to import differences, which I've shown you how to do in this notebook, and then how to apply it to functions to approximate their derivatives. Now you might ask, why do we care about the derivative of a function? I provide, again, the same links or similar parts in this differential calculus one. I provide the link to the applications of derivatives. That's this one right here. The important thing is optimization, at least in the context of this class. So where a derivative is equal to zero corresponds to what is called a critical point of the function. In other words, the roots, meaning where the derivative is equal to zero, the roots of a derivative are the critical points of the original function. What are the critical points? For our purposes, those are the potential locations of maxima and minima of a function, where we might maximize or minimize that function. These points are of great interest in many computational and data science problems. So let's examine the previous example with these points. So point 1, again, we do not need to know the actual derivative of any real valued function f defined on the real numbers. We can just approximate it using the differences module. For example, below we show how to create a user-defined function that uses the differences module to construct an approximation to the derivative of a function f at a value x given a step size h. The only thing you need to know about the step size h is that smaller values of h generally give more accurate approximations of the derivative at x, but there are limits to that, as we saw above, if you make h far too small. So here again is an approximation where you could say, look, I want to create a differences approximation where what I do is I pass it a function f, I give it the values x and h that I would like to approximate the derivative, and then I have a default center difference approximation that I would use, or I can overwrite that and say if you tell me which type of approximation you want is either a forward difference or a backward difference, it will simply just return that approximation. And this is as complicated of a piece of code as you basically need to know how to write to approximate derivatives. So this is like a wrapper function around this module in a manner of speaking. Now the second and third points I made above. Where the derivative is zero is where the function achieves its maxima or minima. Below, and possibly it could be a different point, but we're primarily going to see things where it's maxima or minima. Below, it is a maximum. Pay attention to where the derivative curve crosses, actually we see both, I believe. So I'm just going to delete that. This will be what you get. Pay attention to where the derivative curve crosses the x-axis and where the maximum of the function is. So I will again plot for x values from 0 to 3, and then I'm going to plot two things. I'm going to show you something here. I'm creating a second set of axes on the same plot, and on the left, well, I'm just going to run this and we'll talk about what the code did. So let's look at the at the output, and then we can come back and see how I did this in code. So in blue, I'm showing the actual function again that you saw above, and then I'm showing the finite difference approximation of it in red. The vertical axes, the labels of them on the left are for the function values, and the labels on the right are for the derivative values. And then I plotted, as you can see in this dotted line, the x-axis where the derivative is equal to 0. And if you look at that, where the derivative crosses 0 is where this function had a maximum. And where the derivative crossed 0 again is where the function had a minimum. And then when the function just kind of levels off and becomes flat, well, the lines of tangency are also flat. They have 0 slope, and you see that it's approaching 0. So that was with, when you look at the function I was approximating, I just gave it my function in x. This was using the default values of h in this center difference approximation. You can change this because there's that default value of h. You don't have to change that. You could just say, well, which approximation? And you could change that to, let's say, a forward difference. And you could see it basically gives the same thing. It's reasonably accurate because I defaulted an h value of 0.01, which was giving us reasonably accurate derivatives above. I encourage you to play around with this. Also try the backward difference. And you could try different h values as well. And because I'm keywording them, you can do them in any order you want. So I can make it like 0.2, make it a little larger. And you can see it, it doesn't quite line up because of the error. But if I make h smaller, now it's shifted, and then where that cross 0 seems to line up better with that max. So these are things for you to kind of play with that. You don't have to, but I highly recommend it. If you look at this code, what you see is the first plot, I plot the function in blue. I label the y-axis for that initial set of axes as the function f of x. I also make it in blue so that you can make sense of that f of x. This set of labels of y values correspond to that function. And then I create a twin set of axes on the same axis. For that, and then on that twin set of axes, I'm plotting the derivative function in red, and then I'm setting the y label for it, which is showing up on the right-hand side. I'm making that in red, and I'm saying that's the finite difference approximation of the derivative f prime. And then also for that second set of axes, I want to plot a typical x-axis. So I want to give it a value of 0. I make it align with 1. You can play around with these options. You can make that thicker. You can make this a choice of like 5 if you really want to see that x-axis. There you go. I think 1 and a dotted line in black gives a nice visual of where the x-axis is. So that's basically all there is to that code to plot 2 plots on the same axes, but on the same figure, I should say, the same plot, but with they have different scales, and you don't want the one scale to overwrite the other one. So let's look at points 2 and 3 again. Here's another example with quite a few maxima and minima. So I create a my sine function that has 2 times pi times x. I'm doing the same thing with the twin plots, and I'm using my derivative approximation with the default values of h and the of 0.01 and the center difference approximation, and I plot a typical x-axis. So let's again look at this, and you could see wherever the red curve, which is the derivative approximation of the derivative, crosses 0, is where the other function had either a max or a min value. That's the important thing to take away. And that's why finding the roots of the derivative is often an important part of optimization. And that's also why in the 4th module for the class, the first part A lecture notebook for that talks about root finding problems, because root finding problems come up all the time when you're doing continuous optimization, because you're often trying to find where derivatives are equal to 0. So then let's finish up this lecture notebook talking about modules. Where does the module file need to go? Say you were trying to import a module called spam. You want to import spam. When imported, the interpreter that's trying to import things for the file or the Jupyter Notebook searches for that spam module in locations in the following order. First, it will look for a built-in module with that name. For instance, let's say NumPy was the type of module, it's like a super module, it's a package really. Then it will import that before your module. So you should not create a module that has the name of a built-in package or module that's been installed. Otherwise, it will start to look in the following places. The directory containing the input script, like this notebook, which is where you should put the differences one, as I talked about before. You need to make sure, again, that differences.py is in the same directory on the hub. It's in the same folder as this lecture notebook. And then there's some other options as well that are not pertinent to us, but I give them here for completeness. Now, there's a good question. What happens when you make changes to a module? If you find that you need to edit a function, add a new function, or just make any changes or corrections at all to a module that you want to have, let me zoom out, reflected in your notebook, then you need to do only one of the following. One, you could restart the kernel and rerun all the code cells. By restarting the kernel, you will re-import the module when you run that import the module name as whatever you want to call it. Or you could use the following. You could import the library import lib as follows. Import lib. And then you could run import lib.reload blah, where blah is whatever name you imported your module as. For example, if you want to make changes to the differences.py module that we imported as diff above, then you would run import lib.reload diff. That might seem really weird what I just said, so I'm going to show you an example of this. Let's go to differences.py. Now here this is. And if I say, okay, look, I want to create a new function, which is just my nonsense on X, and I want to return nothing. Okay, so nothing happens. Now I save that. It is now a safe change in that. If I look at diff and I do my autocomplete, here are my three functions. There's a backward difference function, a center difference function, a forward difference function. I don't see my nonsense right here. So I go, oh, you know what? Let me go back to where I imported this. And let's say I just rerun this code cell. So I import differences as diff. Okay, I re-imported the module. No, I did not. Watch what happens again. Here's this diff, and I'll do my tab. That function doesn't show up. And you say, what's going on? I just reloaded. Let me try it again. Let me do it down here. Import differences as diff. Run it again. What happened? Let me do the autocomplete. I only see back diff, cent diff, and forward diff. What's happening? It's already been imported, so every time you rerun this, it's not going to re-import it. It doesn't see the changes. So what you need to do is either restart the kernel, and then you can restart and clear outputs, and you can run through all the code cells again, and then when you import it, the new changes will occur. But that might be kind of annoying for you to do. If you don't want to do that, what you can do is the following. At some point in your notebook, import the import library. And now I want to reload. I've imported differences as diff, so I just need to reload it like this. So I've reloaded it. Now, when I do my autocomplete, now my nonsense is showing up. This is a nice thing to use every once in a while, especially as you're, for instance, in your activity, editing a module and you're constantly having to reload it. It's a good idea while you're doing that to use this import lib function. And then after you've got the module in the way you want it, you don't have to do this anymore. And when you run through the notebook all the way through, everything should work. So that's just something to be aware of. I'm going to go ahead and delete these cells now. And I'm going to remove my nonsense from the differences file. So that leads us to this activity where you have to make and use your own module. I want you to use the main Jupyter tab on your browser where you launch this notebook to create a new text file in the same directory as this lecture. What I mean is this. You come here and then you could say, I want to add, you could either do it through a launcher. So if you go to a new launcher, you could say that you want to make a file, like a text file here. I believe you could run it that way. I typically like to do this. I right click here and I say, give me a new file. Now the default is a text file. I don't want it to be a text file. If you look at a text file, like let me show you what happens here. If I was to just, I won't copy those contents, but let's say I created, again, my nonsense X. Look, it doesn't, I could, look how it looks. It's just this blank text file. It's just kind of not in the formatting or with the coloring that we like with, for instance, like here with all the color, the nice Python visualization of what's going on and the auto indenting and everything. So here's my tip to you. If you look in these instructions, I say, look, go to your 03 lecture notebook part, the part A one, and save the file, copy and paste these functions from it into that file and save it as mymodule.py. I would actually go ahead and save this file first. I'm going to show you, I'm going to delete this stuff here, right click, rename the file as mymodule.py. I think that's what I said to name it. So now I've renamed it as a py file, mymodule.py. Now the text editor recognizes this as a Python file, as a script, a module. So now notice the coloring, right? It starts to look a lot nicer. So now if I say like my nonsense, right? Everything's got that nice kind of look to it. And even when I press return, it does the auto indenting. And so everything has the right coloring. If I add, like a doc string in here, my nonsense function, everything looks as it should, as we're used to it looking when we're writing things in our Python notebooks. It makes the text editor much nicer. So I would recommend saving it as mymodule.py first, and then copying and pasting the myfun1 and myfun2 functions from that lecture notebook. You can also put in some other functions that you like as well to test this. And in fact, save these things first, create some more code cells below, show how you would use these functions imported from your module. So make sure you can show how to import your module, just like I imported the differences. You're going to import my module as maybe my mod. That's what I suggest to do here. Import it as my mod. And then show where we used myfun1 and myfun2 in that part A lecture notebook. Show how you would use them now when they're imported from my mod. So you'd use mymod.myfun1 and then evaluate those functions using some of the inputs we saw in that lecture A notebook. And then I highly recommend trying to import the import lib and reloading this module as you add additional functions to it and showing how you can use them, reload it in and use them. I highly recommend you just go through that process. So that's it for that first main activity in this notebook. And then I describe how packages are really just generalizations of modules here, and you should read about this, but I will end the video here, and then I will have a second video that will give you a gentle introduction to widgets before we conclude the lecture notebooks for the third module. Thanks for listening, and I'll talk to you in a future lecture.